Hi, my name is Wenbo Jiao. For my final project in cs5330, I built and compiled three deep learning architectures for fashion image classifications. The three models are a CNN, a vision transformer, and a hybrid CNN transformer. This project builds on my project 5 work, extending from omniscient digit to the hard fashion omniscient data science. Why fashion omniscient? Fashion omniscient has 10 categories of clothing images. Each image is 28 by 28 pixels in grayscale. There are 60,000 training images and 10,000 testing images. Compared to regular omniscient digit, fashion items are much harder to tell apart. For example, shirt, t-shirt, coat, and pullover all look very similar at this small resolution. CNN have been the standard choice for this kind of image classification task, but with the rise of vision transformers, I want to ask a question. Is the CNN always the best choice, or can transformer and hybrid models offer some advantages? Maybe not in accuracy, but in other areas like noise, robustness, or parameter efficiency. That is the main research question of this project. I designed three architectures. Let me walk through each one. First, the optimized CNN. It has three convolutional blocks. Each block has a 3x3 convolution, batch normalization, and a max pooling. The filters counts go from 30 to 60 to 120. After flattening, there is a fully connected layer with 200 nodes, then a 10-class output. The total parameter count is about 300,000. These settings came from a 40 configuration experiment I ran in Project 5. Second, the optimized vision transformer. Instead of a simple linear patch embedding, use a convolutional patch embedding, a 7x7 convolution with strat 4. This produces 49 patch tokens. I add a CLS token and learnable positional encoders. Then there are three transformer encoder layers, each with 4 attention heights. Total parameters is about 157,000. Third, the hybrid CNN transformer. This is the most interesting design. It has two CNN layers at the front to extract the local features, then reshapes the output into 49 tokens and feeds them into two transformer encoder layers. The idea is simple. The CNN handles local patterns like edge and textures, and the transformer handles how different parts of the image relate to each other. This model is the lightest, only 123,000 parameters. To make a fair comparison, I kept the training setup consistent across all three models. All models are trained for 20 epochs on CPU, with batch size 64. They all use the same data augmentation, random horizontal flips, and small random rotations and shifts. This helps the models generalize better. For the CNN, I use the Adam optimizer with a step learning rate scheduler. The learning rate is cut in half at epoch 10. For the transformer and hybrid, I also use Adam, but with a warm-up schedule. The learning rate slowly increases over the first three epochs, then follows a cosine decay. This warm-up is important because transformer can be unstable at the beginning of training. I also apply gradient clipping to prevent exploding gradients in the transformer component. Now let me show you the main result. Look at the summary table. The thing achieves the highest test accuracy at 92.3%. The hybrid model is second at 90.4%, and the pure transformer is third at 88.2%. This ranking makes sense. CNN have a natural advantage on small 28 by 28 images because their convolutional structure is designed for local pattern recognition. The hybrid model outperforms the pure transformer by more than 2 percentage points while using fewer parameters. This shows that adding a CNN front end really helps the transformer. If you look at the training curves on the right, the CNN converges the fastest, reaching 90% accuracy by epoch 7. The transformer improves slowly but steadily. The hybrid starts slow during the warm-up phase, then catch up quickly. One more thing to notice, the CNN has the most parameters at 300,000, but the hybrid achieves 90% accuracy with only 123,000. So the hybrid is the most parameter-efficient model. Let me break down the result by class. On the left, you can see the per class accuracy for all three models. Most categories are above 90%, like trousers, sandals, sneaker, and bag. These items have distinctive shapes, so they are easy to classify. But look at the shared category. All three models score only around 64 to 67%. This is by far the hardest category. The confusion matrix on the right show why. Shirts are constantly confused with t-shirts, coats, and pullovers. At 28 by 28 resolution, three items genuinely look alike. This is a limitation of the dataset itself, not a failure of any specific model. The CNN has the tightest diagonal in its confusion matrix, which is consistent with its highest overall accuracy. Now, this is the most surprising and interesting finding of the entire project. The transformer is dramatically more robust to noise than the CNN or the hybrid. Look at the numbers at the top. When I add Gaussian noise with standard deviation 0.3, the transformer still holds 82% accuracy, but the CNN drops to only 54%, and the hybrid drops even further to 42%. That is nearly a 30% point difference between transformer and CNN. The same pattern appears with random occlusion. When I randomly mask 30% of pixels, the transformer keep about 51% accuracy, while the CNN drops to 37%. So why does this happen? Because self-attention looks at all parts of the image at the same time. When some pixels are corrupted, the other uncorrupted regions still contribute to the final decision. The noise gets averaged out, but CNN processes small local window. When you corrupt a few pixels, it directly damages the local features, and that damage cascades through the pooling layers. One unexpected result is that the hybrid actually does worse under noise. The CNN front end seems to amplify the noise before the transformer even gets to see the tokens. Finally, let me show some feature visualization. On the left, you can see the CNN first layer filters. They learn to detect the edge, textures, and simple patterns. Different filters activate on different parts of the clothing. In the middle, the transformer attention map show how the model focuses attention. In the early layers, attention is spread out everywhere, but in the deeper layer, it focuses on meaningful regions like necklines on shirt and soles on the shoes. On the right, the T-SNE plots project each model's internal features into 2D. The CNN produces the tightest and most separated clusters, which explain its highest accuracy. The transformers clusters are more spread out, and the hybrid falls somewhere in between. So to conclude, there is no single best architecture. It depends on your priorities. If you want the best accuracy on clean images, use the CNN. If you are dealing with noisy or degraded images, the transformer is far more robust. And if you have limited resources and you need a compact model, the hybrid gives you 90% accuracy with only 123,000 parameters. Thank you. That is the end of my conclusion.